Welcome back to the session on power series solution of ordinary differential equations. If a differential equation contains the variable coefficients, then the solution is not in a closed form. For such equations, the solution contains infinite terms in the independent variable x. Here we shall discuss the power series method to find a solution of a second order differential equation. The general format is a naught of x into y double dash plus a1 of x into y dash plus a2 of x into y is equal to 0. First of all, we have to define a power series. An expression is of the form c naught plus c1 into x minus x naught plus c2 into x minus x naught square plus etc. in general cn into x minus xn whole raised to n plus etc. Or in summation form we can write this as summation cn into x minus xn whole raised to n, where n varies from 0 to infinity, is known as a power series of the variable x in powers of x minus x naught. So here there is a correction, these all are x naught. This expression is known as the power series of the variable x about the point x naught. The constants c naught, c1, c2 etc. are known as the coefficients, and this x naught is known as the center of the power series. Here n takes only positive integral values. Therefore, this power series does not contain negative or fractional powers. So, the power series contains only the positive terms. Now, we have a theorem. If x naught is a regular point or an ordinary point, regular point means an ordinary point of this differential equation, then a general solution of this differential equation is obtained as a linear combination of two linearly independent power series solutions of the form summation n varies from 0 to infinity cn into x minus x naught all raised to n. These two power series both converge in some interval modulus of x minus x naught less than r. Here r is greater than 0. Now, let me explain the steps involved in the power series method. First of all, we assume that y is equal to summation cn into x minus x naught all raised to n, where n varies from 0 to infinity, be the solution of the given second order differential equation. Then we substitute y dash, y double dash and this y in the given differential equation, then collect the coefficients of like powers of x minus x naught. This converts the differential equation into the form k naught plus k1 into x minus x naught plus k2 into x minus x naught the whole square plus etc. is equal to 0, where ki for I equal to 0, 1, 2, 3 etc. up to infinity are functions of certain coefficients Cn. The third step is we can write all these ki's equal to 0, because if this is a solution, then this will satisfy the given differential equation, means all ki's must be equal to 0. That means k naught equal to 0, k1 equal to 0, k2 equal to 0, and so on. Then we solve these equations to obtain the unknown coefficients Cn's. Generally, this leads to a recurrence relation between Cn's, which helps to determine unknown coefficients in terms of the other known coefficients. The Cn's are determined by equating to 0 each powers of x minus x naught. Then we substitute these Cn's in this first expression to get the required power series solution of the given differential equation. These are the steps involved in the power series method. Now consider the differential equation d square y by dx square minus y is equal to 0. This is a second order differential equation. Here p of x is equal to 0 and q of x is equal to minus 1. Both are analytic. That means both are analytic at x equal to 0. Therefore, we can say that x equal to 0 is a regular point or an ordinary point of this differential equation. Therefore, we can write all the solutions in the form y is equal to c naught plus c1 into x plus c2 into x square plus etc. Let it be named as equation number 2. The given equation is 1. The remaining terms are c3 into x cube plus next term is c4 into x raised to 4 plus etc. Therefore, dy by dx is equal to c naught is a constant, therefore derivative is 0. Here derivative of c1x is c1 plus c2 into x square means derivative is 2c2x. Here 3c3 x square 4c4 x cube plus etc. And d square y by dx square is equal to 2c2 plus 3c3 into 2x means 6c3x plus here 4 into 3 is 12, 12 into c4 into x square plus etc. Now, we substitute these values, that is y y dash means dy by dx, and the second derivative d square y by dx square. In this given differential equation, we can write as 2c2, that is the given differential equation will become 2c2 plus 6 into c3x plus 12c4 x square plus etc. This is d square y by dx square minus here y means c0 plus c1x plus c2x square plus c3x cube plus etc. equal to the right hand side is 0. That means we can write this as, here 2c2 is a constant term, in this c0 is a constant term, therefore we can combine the two constant terms 2c2 and minus c0 plus here the coefficient of x is 6c3. In this term the coefficient is c1, therefore we can combine the coefficient of x as 6c3 minus c1 into x. Similarly, for x square, here 12c4 minus c2 into x square plus etc. equal to the right hand side is 0. Here the right hand side 0 means 0 plus 0x plus 0x cube plus 0x raised to 4 plus etc. All the coefficients are 0. Therefore, we can equate the corresponding terms. We will get 2c2 minus c0 is equal to 0. From this 6c3 minus c1, which also equal to 0 because in the right hand side all the coefficients are 0. From this we can write 12c4 minus c2 is equal to 0 and so on. From this we can write c2 equal to, from this first equation we can write c2 equal to c0 divided by 2. That is, c2 can be expressed in terms of c0. From this expression we can write 6c3 is equal to c1, means c3 is equal to c1 divided by 6. From this we can write 12c4 equal to c2, that means c4 is equal to c2 by 12. From the next term means here 12 c4 x square. Next is, if we write the next terms, we can write here c5 x raised to 5. Therefore, when we differentiate this, we get 5 c5 x raised to 4. The next term is c6 x raised to 6. The derivative is 6 into c6 x raised to 5 plus etc. Therefore, here 4 into 5 is 20 into c5 x cube plus here 5 into 6 is 30 c6 x raised to 4 and so on. Therefore, when we equate to 0, we get the next term as here 12c4 minus c2. Therefore, next term is 20c5 minus c3, that is the coefficient of x cube is c3, which is equal to 0. The next is 30 c6 minus, here the coefficient of x raised to 4 is c4 equal to 0 and so on. Therefore, we can write C5 as C5 is equal to C3 divided by 20 and C6 as C4 divided by 30. That means we obtained C2 as 1 by 2 into C0, C3 as 1 by 6 into C1, C4 is C2 by 12. But C2 is 1 by 2 into C0. Therefore, we will get this as 1 by 2 C0 divided by 12 means 1 by 24 C0. C5 is equal to C3 by 20. C3 is 1 by 6 C1 divided by 20 means 120. C1 120 divided by C1, sorry 120 into C1 which is C5, and C6 is 1 by 30 into C4, but C4 is 1 by 24 into C0. That means 1 by 24 into 30 C0, etc. Therefore, we can write the solution as y equal to C0 plus C1x plus C2 is 1 by 2 C0 plus here into x square. Next is C3, that is 1 by 6 C1 x cube plus C4 x raised to 4 means 1 by 24 C0 x raised to 4 plus C5 x raised to 5 means 1 by 20 into C1 x raised to 5 plus etc. Here C5 is 1 by 120 into C1. Therefore, here 1 by 120 into C1 x raised to 5 plus etc. Now, we can combining all the terms having C0 and then all the terms having C1. We can write the solution as y is equal to C0 into 1 plus 1 by 2 x square plus here 1 by 24 x raised to 4 plus etc. plus C1 into x plus 1 by 6 into x cube plus here the terms containing C1 is 1 by 20 into x raised to 5 plus etc. which is equal to, we can write this as y is equal to C0 into 1 plus 1 by 2 means we can write 1 by 2 factorial, that is x square by 2 factorial plus here x raised to 4 in the numerator, in the denominator it is 24. We can write 24 as 4 factorial plus etc. plus C1 into here x plus x cube divided by the 6 can be written as 3 factorial plus x raised to 5 divided by 120 can be written as 5 factorial plus etc. That is, this is equal to C naught into this series is the expansion of cos hx, the hyperbolic cosine cos hx, plus C1 into this expansion is sin hx, C1 into sin hx. Therefore, we will obtain the required solution of the given differential equation as y is equal to C naught into cos hx plus C1 into sin hx, that is the linear combination of two hyperbolic functions cos hx and sin hx. Since the given differential equation is of order 2, the solution will contain two arbitrary constants. Here the two arbitrary constants are C naught and C1. This is an example for the power series method of finding the solution of a second order differential equation with the variable coefficients. Now, let me explain the Frobenius method of finding the solution of second order differential equations with the variable coefficients. In power series method, the solution y is equal to summation Cn into x minus x naught the whole raised to n, where n varies from 0 to infinity, was obtained only when x naught is an ordinary point of the given differential equation. Solution near regular singular point x naught can be obtained by an extension of the power series method, which is known as the Frobenius method or the generalized power series method. Frobenius method. This is a generalized power series method. In this method, we consider a series of the form modulus of x minus x naught raised to r into summation n varies from 0 to infinity Cn into x minus x naught raised to n, which is known as Frobenius series. Here r is an unknown constant to be determined. R is a constant which is to be determined. The Frobenius method is based on the theorem, let x naught be a regular singular point of the differential equation y double dash plus p of x into y dash plus q of x into y double dash into y is equal to 0. Then this differential equation has at least one non-trivial solution of the form y is equal to modulus of x minus x naught raised to r into summation over n varies from 0 to infinity Cn into x minus x naught all raised to n, which is convergent in some deleted interval about x naught, that is 0 less than mod x minus x naught less than r, where this r is greater than 0. The first step in the Frobenius method is we assume a solution of the form modulus of x minus x naught raised to r into summation n varies from 0 to infinity Cn into x minus x naught all raised to n for this second order differential equation with x naught as a regular singular point. The series is valid in this deleted neighborhood 0 less than mod x minus x naught is less than r. Here the exponent r is chosen so that the coefficient c naught not equal to 0. that is the highest possible power of x is factored out. If C0 not equal to 0 means the highest possible power of x is factored out. And the step 2 is we substitute the value of this y dash and y double dash in the given differential equation and collecting the coefficients of like powers of x minus x naught. Then the given differential equation takes the form k naught into x minus x naught raised to r plus 1 plus k1 into x minus x naught raised to r plus k plus 1. Here not r plus 1, this is r plus k. The next term is k2 into x minus x naught raised to r plus k plus 2 plus etc. Here the coefficients ki for I equal to 0 1 2 3 etc. up to infinity are functions of the exponent r and the constant coefficients Cn. Also this k is an integer. The third step is we can equate to 0 all the coefficients ki's, that is k naught equal to 0, k1 equal to 0 etc. up to infinity equal to 0. Here k naught is the coefficient of the lowest power r plus k of x minus x naught. The equation k naught equal to 0 is a quadratic equation in R, which is known as the indicial equation. Corresponding to the given differential equation. The roots of the indicial equation means it is a quadratic equation and there are two roots, namely R1 and R2. These two roots R1 and R2 are known as the exponents of this expression y equal to mod x minus x naught raised to r into summation cr into x minus x naught raised to n, and are the only possible values for the constant r in the assumed solution. Generally R1 is taken as the larger root so that R1 is greater than R2. The fourth step is when R is known, solving the equations k1 equal to 0, k2 equal to 0 etc. we determine completely the unknown coefficients Cn's. And the fifth step is let y1 of x and y2 of x be two non-trivial linearly independent solutions of the given differential equation. Then the general solution is y of x is equal to a into y1 of x plus b into y2 of x. We can write the general solution as a into y1 of x plus b into y2 of x, where a and b are the arbitrary constants. Then with the non-exponent r and the non-coefficient Cn's, y1 of x, that is one of the two solutions can be written in this form, that is y equal to modulus of x minus x naught raised to r into summation n varies from 0 to infinity Cn into x minus x naught raised to n. The form of the second solution y2 of x may be similar to this form or may contain a logarithmic term, and the general solution depending on the root of the indicial equation R1 and R2. Now let me conclude this session. In this session we discussed the power series method of finding solution of second order differential equation with variable coefficients, and we discussed the Frobenius method for finding the solution of second order differential equation with variable coefficients. Thank you for watching this class. Have a nice day.